My name is Muhammad Irfan Hilman bin Aziz. My matrix number is 2213022387. So today I would like to present our assignment 2 task, and our chosen topic is digital modulation. And my part is to explain about quadrature amplitude modulation, or we can call it as QAM. So what is QAM? QAM is actually a combination of two modulation techniques, which are amplitude shift keying, RSK, and also phase shift keying, PSK. It combines amplitude modulation and phase modulation by varying both amplitude and the phase of a carrier wave to encode the information. Also, it can be represented by a constellation diagram with amplitude phase combination. QAM also can determine the maximum bit per symbol using the states given. For example, if we have 8 states, we can use the formula of m equals to 2 to the power of n, and when we derive or we substitute the value, we can get the number of maximum bits per symbol transferred. And for this question, we got 3 bits per symbol, meaning that we can go from 000 up until 111. Then why do we need QAM actually? We need QAM actually to increase the spectral efficiency by transmitting more data in the same bandwidth. Other than that, we also can balance the power efficiency and also bandwidth efficiency. We can also meet the growing demand for high-speed data in applications like Wi-Fi, LTE, and also broadband. And the last one is it is adaptable to channel conditions, choosing modulation order based on signal quality. Then if we look at the last panel, which is constellation diagram, I have put three pictures that differentiate from one another. So the basic one is 16 PSK, just like we all know, in phase shift keying. But there are two other ways to improve this modulation technique by doing 16 amplitude phase shift keying, or also 16 quadrature amplitude modulation. So why these two vary from each other? It varies from each other because it has different purposes that they serve. Therefore, they have a few trade-off between QAM and also APSK, and some of the trade-off are spectral and power efficiency, also noise sensitivity, application, as well as constellation diagram. So QAM actually prioritizes spectral efficiency for high-speed data transmission in linear, high SNR environment, while APSK focus on power efficiency and robustness in non-linear environments. Then, for the advantages of QAM, it has high spectral efficiency, just like I said just now, by utilizing the both amplitude and phase variations to transmit more data per unit bandwidth. Next is flexible for the adaptive modulation. It can dynamically adjust modulation order based on channel condition. And the last one is supports high data rate by enabling the transmission of large amounts of data. For the disadvantages, it is sensitive to noise because the constellation points are closely spaced, making QAM vulnerable to noise and interference. Also, it has power efficiency. It requires high linear amplifier, therefore more power are needed. And last one is complex receiver design. It requires sophisticated equalizer and error correction to handle inter-symbol interference. And last one is the application of QAM. It can be used for wireless communication, such as Wi-Fi standard like IEEE 802.11a for high data rates. It also can be used it is also a key technology in cellular networks like 4G LTE and also 5G. Then the next one is it can also be applied in digital television, like it is being used in cable TV system like DVB-C to transmit multiple channels over a limited bandwidth. And lastly, it is used in SDR system for adaptive modulation based on channel conditions. So as you can see, QAM actually offers a lot of things, and is much more better than the basic tree of other modulation, ASK, FSK, and PSK. Therefore, it is usually worldwide for a lot of applications, especially in wireless communication. Therefore, that's all for me. Thank you.
Hello, I'm Muhammad Fairuz bin Imran. Today I will present about phase shift keying, PSK. So, in today's digital world, communication technologies form the backbone of our interconnected lives. From sending a message to streaming videos, digital modulation ensures seamless transmission of data. One of the key techniques in digital modulation is phase shift keying, or PSK. In this video, we will explore how PSK works, its practical application, and why it's vital for modern communication system. So, phase shift keying is a method of digital modulation that encodes information by altering the phase of a carrier wave. Simply put, PSK maps digital bits 0 and 1s to change in the phase of a signal. Let's start with the simplest form, binary phase shift keying, or BPSK. Okay, in BPSK, each phase shift represents a single bit. For example, when the binary input is 1, the phase remains at 0 degree. So when the input is changed to 0, the phase flips to 180 degree. Start from here. So when the binary input is changed to 1, the phase flips to 0 degree again. Okay. So when the input still remain 1, the phase still remain at 0 degree. Now let's take it a step future with quadrature phase shift keying, or QPSK. This method encodes 2 bits per symbol by using 4 distinct phases: 0 degree, 90 degree, 180 degree, and 270 degree. With QPSK, we double the data rate compared to BPSK while maintaining the same bandwidth. This efficiency makes QPSK popular in applications like Wi-Fi and satellite communication. The PSK modulated signal is mathematically represented as where R is amplitude of the wave, FC is the carrier frequency, delta is the phase shift based on the input bits. So using this formula, we can visualize the waveforms and constellation points for both BPSK and QPSK, helping us understanding how data is encoded efficiently. PSK finds application in many real-world systems. For example, Wi-Fi standards using QPSK for reliable data transmission. Satellite communication relies on PSK for its robustness over long distance. RFID tag use PSK for efficient asset tracking. The key strengths of PSK are its spectral efficiency and resilience to noise, making it a go-to choice for various communication technologies. In summary, PSK encodes data by altering the phase of a carrier signal. With its simplicity and efficiency, PSK plays a vital role in ensuring reliable communication in technologies we use every day. From streaming your favorite shows to satellite connectivity, PSK makes it all possible. Thank you for watching, and I hope this explanation of PSK has been informative.
Assalamualaikum. My name is Aiman Azrie bin Hashim. My metric number is 2213022373. And my part will be presenting technique of FSK in digital modulation. So FSK is shortened form for frequency shift keying, where the technique uses the frequency of carrier signal to vary in order to represent the bit for input 1 and 0. So there will be two frequencies of carrier signal to represent the bits 1 and 0 respectively. Therefore, the bandwidth becomes larger than alternative methods. Some variables remain constant, such as the amplitude and the phase of the modulated signal. And then there are three types of FSK. The first is binary FSK, the next is multi-level FSK, and the third is minimum shift keying MSK. On the next slide is the waveform and the formula of FSK. The image below, on the right side below, is the waveform for FSK, and the image above is the formula for FSK. So VC is the carrier voltage, which is the amplitude of the signal, of the carrier signal, and FC is the frequency of carrier signal, and VM is the amplitude for message or modulating signal, and delta F is the deviation frequency, which will be explained in the next slide. So here is the baud rate for FSK, where N is equals to N baud. So N is the bit rate and N baud is the baud rate of the signal. So it is shown that N bit rate is equals to the baud rate. And the next slide is the bandwidth of FSK. So the bandwidth is the difference between carrier signal 1 and carrier signal 0 and plus the N baud. So the bandwidth will be larger because it will use two frequency to represent the bits of input signal 1 and 0. Next slide. This is the frequency deviation. On the first image is the formula, which is Fm minus Fs in modulus over 2. And Fm minus Fs is the difference between Mach and space frequency. The second image is the positive delta F, which is for logic 1, and also the negative delta F, which is used for logic 0. Frequency deviation can be seen on the third image, where the Mach frequency is the binary digit 1 and the space frequency is used for binary input 0. On to next slide. The application of FSK are used in technologies such as modems, RFID systems, and low power communications such as walkie-talkies. And FSK can be compared to PSK, ASK, and QAM, which are alternative digital modulation techniques. In terms of representation, FSK only varies the frequencies to represent bit 0 and 1. And then the noise immunity is high compared to others due to resistance to amplitude noise. The bandwidth efficiency is low because the use of two frequencies from carrier frequency, and complexity of implementation is low because of the use of simple hardware. The error rate is low in noisy environment compared to others. So the examples of use are different compared to others because of the characteristics of FSK. Now we move on to application in Scilab. So I will open SciNotes to apply FSK in order to output a waveform. So the formula, the input signal, I will use 1/4 times 100 to represent bits 1000, and the amplitude will be 5, and also the frequency carrier will be modified. From here I will use 10. The frequency deviation I will use 0.5, and the output will be like this. From the output waveform, we can see that the high frequency is used from the bits 1 from input signal, and the low frequency is used for the bit 0 from the input signal. So we can see the difference in frequency to represent the digital signal of the input. So that is FSK, frequency shift keying. That's all from me. Thank you.